Hi everyone and welcome to this new video about AC steady state power. And we continue with the design examples. This is our design example number 2. The following is given. There is an industrial plant which operates from a source of 800 volts RMS with a frequency of 50 Hz and has two loads connected in parallel to this source. So the industrial plant has two loads and it's connected to this source with this frequency. Okay. One of the loads draws 70 kilowatts at a power factor of 0.5 lagging, and the other, the second load, draws 40 kilowatts at a power factor of 0.9 leading this time. Okay, so the question in place is the following. Determine the value of the required parallel element connected to these loads to correct power factor to unity. So actually, first, maybe this is a better starting point. Just make a sketch of the situation. So what do we have? What is actually given pictorially? So let's start with that. Okay, let's make the drawing. So there is a power supply, Vs, which is connected to these two loads. So I just make it general Z1, the other one as Z2, so these are two loads, and there is a parallel element required to compensate the power factor or to make the power factor unity. So I will place a parallel element, which I don't know yet what it is exactly, but I can already say that this Z something, and I denoted as Z subscript P. So I'm looking for the value of Z of P. So what can I say about the loads? So we have Z1 and a Z2. I can say the following for Z1. I can say that the S1, which is a summation of the true power, or the real power, plus the JQ1. You might ask, why is it plus and why not minus? Because the first load, I'm considering this one, has a power factor of lagging. So there's 0.5, but this is lagging. So if it is lagging, that is an inductive load. So you have also the Q, which is positive. So you can already know that the situation is for load 1. For load 2, I can write a similar expression, P2, but this time it is leading. So there is a capacitive in a load, so there will be minus JQ2. Okay, this is actually the situation for the two loads, and the apparent powers are given for S1 and S2 in this fashion, and I would like to determine, of course, Z of P. So let's make this also clear. This is the question place here. So let's make a drawing of the situations using the values given above. So first, for the first load, I have the following power diagram. So I can draw the following power diagram. So the real axis and imaginary axis, we already know this from the previous examples and the videos. So we have the real part of the power, which is P1, and I have also the imaginary part, so the reactive part. And this will, of course, result in an apparent power S1 with the associated theta 1. Okay, and again, the same story holds for the second load. So this is load 1. So I will make this clear. This is load 1. So make this also the same, similar drawing for load 2. So we have here again the imaginary axis and the real axis. Imaginary and real. Okay, and there is also a real part of this and an imaginary part of, there's of course P2, this one, and this will be pointing downwards, so in the negative direction, so there will be minus Q2, and the summation, factorial summation, will result in a apparent power of S2. Okay, so this is the value for this, and associated, of course, the theta 2. So let's look at the given values again. There is 70 watts for the first load, so that means actually this one is 70,000. So 7 times 10 to the power 4, and this will be for the load 2, it will be 40,000. So that will be 4 times 10 to the power 4. The theta 1 and the theta 2 can be calculated very easily using the power factors given. So let's do that also. So that's also interesting. So the first one, theta 1, will be the arc cosine of the power factor of the first one. And the power factor of the first one will be 0.5 lagging. So that means actually the following: arc cosine of 0.5, which will result in 60 degrees, exactly 60 degrees. And if I do the similar for theta 2, it will be arc cosine of power factor of 2, and the power factor of 2 will be 0.9 leading, so that is lagging, this will be leading, and this will result in arc cosine of 0.9. And because it is leading, what do we need actually for leading? We need actually minus for the theta, so that is very important. So 0.9, fill it in, and you will get 26 degrees, of course, but because it's leading, you have to make sure that there's a minus sign, and there's minus 26 degrees. That's actually for this, and this for the first load. Let's let it zoom out. Okay, so that's actually the situation, and let me make this clear for lagging. Okay, now what do we do next? Now we would like to, of course, determine the value of the ZP, of course, the element itself also. It is maybe inductor, maybe a capacitor, depending on actually the total effect. So in total, we would like to have a unity power factor. So what I want to calculate first is what is the Q1 and the Q2. Using the Q1 and the Q2 values, I can subtract, use the difference between them, and to come up to a Q in total in effect of 0. So what I want is, I would like to move on to what is the Q total in this case, which is Q1 minus Q2, because I don't know the Q1 and the Q2. So for calculation of the Q1, I can use this diagram, and for Q2 I can use this diagram using the thetas and the given values for the p's. So let's do that. For Q1, I can use a geometry here, and I can use tangent. So tangent of the theta 1 will be Q1 divided by P1. So if you rewrite this in terms of Q1, you will get P1 times tangent of theta 1, which will be 7 times 10 to the power 4, which will be 70 kilowatts, times the tangent of 60 degrees. And this will give us approximately 12.1 times 10 to the power 4 volts amperes. Okay, that's actually the situation for Q1. What is the situation for Q2? For Q2, exactly the same procedure. Do the P2 times the tangent of theta 2, which will be 4 times 10 to the power 4 times tangent of, and you will of course take the minus sign, but you will get a Q which is a minus. So that's actually the situation for this case. So you will take the absolute value of that, so that will be here 26. So what we have is the 1.95 times 10 to the power 4 volt amperes. Okay, now from here I can move on and calculate Q total, which is 12.1 times 10 to the power 4 minus 1.95 times 10 to the power 4, which will result in 10.15 times 10 to the power 4 volt amperes reactive. Now is the question, what is actually the required element? Is it the capacitor or the inductor? Now, since I know that this one is larger than this one, I will need to reduce actually the net arrow. So the net arrow is this large, but it's still in the positive direction. I can already see that because this is pointing in the positive y-axis of 12.1 times 10 to the power 4, but this arrow Q2 with this one, this is of course not to scale, just to give you an impression, just only 1.95 times 10 to the power 4, so which is much smaller than this one. So in effect I'm still pointing in the positive y direction in the imaginary axis, so I have to reduce that. I can only reduce it going down using a capacitor. If I use the inductor, I will make it only worse. So I can use a capacitor here. So I already know I need a capacitor. So Q total is positive. Thus we require a capacitive compensation. Okay, so let's move on. What is actually the situation then for the capacitor? The capacitor, which is the added capacitor Q of C, will be of course equal to the Q total, which is what we have here, 10.15 times 10 to the power 4 volt amperes reactive. And I know of course if this is a parallel connection for this element, which is now only a capacitor, this will also have the same voltage, which is 800 volts RMS. So remember, this is already given in RMS. I don't have to divide by square root of 2, which we did in the previous examples. So that is actually in this case not necessary, not required. So what we have is the following: Q of C will be the voltage source in RMS squared divided by the reactance of this capacitor. So from the reactance I can calculate of course the value of the capacitor. So let's move on. So this will be 10.15 times 10 to the power 4, which will be 800 quantity squared divided by Q of C, and I will get a Q of C of approximately 6.305 ohms. Okay, now I can use of course the same formula. Q of C is equal to 1 over omega times C. Now I can now substitute the values. This 6.305, which is equal to 1 over omega. What was the omega? Omega is 2 pi times the frequency, and the frequency was 50 hertz, which is given here. So I can move on by using the omega as 100 pi. So 100 pi. So I will get the following: 1 or 2 pi, I will make it clear, 2 pi times 50, which is actually the omega here, times C. So I can now calculate the capacitor value, which is close to 505 microfarads. So if I use a capacitor here, I will have the power factor reduced, or I mean corrected to unity or to 1. Just to give you an impression, what is actually this circuit all about? So actually this is an inductive circuit, this is an inductive load, and this is a capacitive load, and it is just a capacitor. So if I just open up all those impedances, just to give you an impression, actually the design is now complete. So this is just extra information. So I have the first load, which is an inductive load. So there is some resistor modeled with a series inductor. This is the situation, so I have the voltage source still here. And the further second load, I have the resistor R2, some resistor we don't know, it is also not necessary for this calculation. And there is also a capacitor, so there is a capacitor C2, just to mention there's a second load. And now the red one, which was the element which is now placed in parallel, is the capacitor C, and this is 505 microfarad. So this one, I will give it in green. This is the load 1, and the other one is load 2. And this is the complete situation actually for this example. So we have designed the circuit, given a specification for the power factor, corrected to the unity, and for this load we had the power, the true power, and also the power factor, and we have specified or calculated the value for the C such that the power factor is unity. This was for design example number 1, for considering the subject of AC steady state power. So we will move on, keep in touch, and see you next time, and take care.